Good evening, Professor. This is my today personal timetable. Today I am going to present the thesis, the two theses that you have gave. So let's begin. The first thesis name is a microwave radiometer for internal body temperature measurement. In this, the second chapter. In the previous presentation also I have mentioned this chapter 2 radiometer design, but I'm just summarizing quickly with this. In radiometer design simplified, it is a block diagram, a total power radiometer along with the important parameters such as gain stand as a G and bandwidth stand as a B. The power is detected with the square law detector x square and integrated with an integration time, and the power is received through the antenna and equivalent noise temperature, and the bandwidth is generally, and in this bandwidth is generally is dedicated by the filter used in the prediction section of the receiver, but is also a function of bandwidth of active components such as amplifier and square law, and the out and the gain which is detected by the number of amplifier in the receiver chain, and losses in the receiver from passive element such as transmission line and filter, and then the output is integrated with the time constant t to improve a radiometric solution. And next was the this is an equivalent noise temperature definition, where a noise device, in the first figure you can see that a terminated in a fiction 0 Kelvin loaded is placed by a noiseless device, and as you can see in this second figure, terminated is a resistor with an equivalent noise temperature. Now considering this two figure, the network from A figure is a noise amplifier, uh, 0 Kelvin, as I said before. For this case, the represent of the output noise power generated by the device when the input is connected to the noise free termination. This network is replaced with an equivalent noiseless network shown. And as you can see in figure B, represent an equivalent temperature of an match resistor referred to an input of the noise free device that will generate the same output power. This is the receiver architecture. As you can see in this, a DIC radiometer block diagram where the input of the radiometer is periodically switched to a match reference load at a stable temperature. To reduce this, now I'm going to explain this. To reduce the DIC, proposed a radiometer that is periodically compared to the match reference to load a stable temperature, as you can see in this figure, and then output gets synchronized demodulated, resulting is the output stable temperature. This is the balanced noise injection DIC radiometer block diagram. As you can see, this is the method of balancing include varying the reference load with the variable attenuator until the reference temperature is equal to the antenna temperature. Another method was balancing the radiometer is to inject the variable amount of noise by means of coupler into the antenna path to raise the antenna temperature to be equal to the reference. Balance technique require a feedback to control the attenuator until a balanced mode of operation is achieved. This is the now I'm this is the receiver and the probe design for variable radiometer. This is the general calibration line. In this you can see that I have as you can see in this general calibration line, there is in the first figure, that is A figure, the radiometer where the volt H and volt C, them that are hot and cold output voltage corresponding to the input temperature, that is TH and TC, and two load radiometer. And as you can see in this the second figure, there is a radiometer is constantly calibrated using a RF switch at the front of a receiver. Now I'm going to explain this. There was a table in this thesis, in this chapter, uh, that receiver frequency for variable radiometer. The frequency band choose a protected of radio astronomy and remote sensing. There is a passive sensing frequency band, abbreviator name. uh, in this reserved of radio astronomy at specific location, emission of prohibited at frequency that ranges from 1.4 to 1.427 gigahertz. The part of the frequency band is shared with the transmitter. Emission are prohibited by the FCC in frequency range of that ranges from 4.99 to 5.0 gigahertz. Now this is the calibration in this. Now as you can see, this is the calibration, the post detection data condition and equation. The DC volt is applied and filtered before is being measured with DAQ. In this there is a two load radiometer. Calibration is performed continuously by regularly switching the receiver between the antenna and that two load, as you can see, of known temperature. Now the output of the from the square law detector is amplified by a low noise, filtered and then measured by an analog to digital converter ADC. The AD620 from analog device is a low noise instrumentation amplifier requiring only one resistor to set gain between 1 to 10,000. After amplifier a RC low pass filter is used, then the voltage is measured by a national instrument. And then the DAQ is there is a DAQ in this figure is also used to control RF front end switch for calibration. This setup is illustrated in this figure. Technology and the temperature data logger TC08 from Pico technology to monitor the load temperature and experimental test setup temperature. And using all this all these things are used in this calibration part. And now the next is I am going to explain this figure. This is the raw measurement data used to determine antenna, and the raw hot antenna and cold voltage are averaged every temperature scale to ensure an accurate estimate of the mean of each standard. For the first 10 low pass filter, time constant shown in the insert are thrown out. And in this I have also summarized that they had used uh, custom code written was in Python that is a software part to detect the data, and after detecting the data, processing periodically, then using a Python technology and rewrite the raw time series data. This was done every 30 seconds without interrupting data sampling, so that the data used for calculation is continuous. As it was mentioned in this thesis, they have used a Python technology. Now I'm going to explain 1.4 gigahertz system. In this, I have in this chapter, there was a section that 1.4 gigahertz that and now I'm going to explain this figure as I have mentioned in this presentation. As you can see, the figure first, that is 2.9. um, the receiver and detector sensitivity are measured using a lock-in amplifier, and this is like the history. I'm just explaining the history first. That is, a stocky diode is matched with a plumped element, LC matched, shown in the figure first, and with the corresponding element shows that you can see in the table, the a photograph of a square law detector that is in figure B. And when you see in this table, there is a C, a symmetric element, and manufacturer etc, and part number is this, value is 4.7 ph, and all this. As you can go through this table, this is a symmetric element and a diode detectors, sorry. And next is this, as you can see, there is a graph in this that measure performance of 1.4 gigahertz diode, that is, as you can see in this first figure, that is one second, so just I'm summarizing. The output is in voltage versus input or at 1.4 gigahertz. It in both in three graph that is mentioned. And in the first graph, it that is a demonstration of sensitivity of 25 meter volt upon volt, and the narrow band. And in the second figure, that is B, is a broadband. And in the third figure, there is a frequency response is shown of an input power of minus 40 decimal. And next is this is this is a prediction schematic of uh, uh, just a second, I have been very fast. This is this is the next 2.7 gigahertz system. As you can see in this system, there is a as this is the another system that is 2.7 into 1.4 gigahertz. They had also uh, simulating, they had used a software HFS. And I have given further detail of HFS on Roger 44350B. And now I'm going to explain this 2.7 gigahertz system. It is a receiver was designed using a same method as it was designed in previous 1.4 gigahertz receiver design. In this uh, there is a 2.7 gigahertz detector was designed using a single stub match with a grounded co-panel waveguide transmission line of on a RF4 substrate. RF choke was designed by Mendring RF sorted, and this was uh, developed and researched in the same uh, institute like Skyworks, and Stocky diode was used to categorize as was the as same used in the previous system 1.4 gigahertz system. And as you can see in this figure, that is this is a performance of 2.7 gigahertz diode square law detector. The first graph you can the first image, as you can see, there is a output voltage versus input at 2.6 65 gigahertz demonstrate sensitivity of 10 milliwatt and the narrow band, and the figure C is broadband, and you can see in figure D is a frequency response in as shown for an output power of 40 dBm. Now this is same that uh, prediction schematic of 2.7 gigahertz radiometer. As you can see in this figure, that a radiometer consists of a switch at input. There is a switch at input of for calibration, then a series of LNA are cascaded with band pass filter to achieve the required gain, and the filter outside of band uh, of interest. Um, this is the next was that, as you can see in this table, the element is categorized, and schematic is summarized, what which software, hit software, manufacturer name, and the part name, and the gain, and the NF noise frequency name, all the frequency data, whatever is used in this 2.7 gigahertz radiometric prediction schematic is used. The component is used for 2.7 gigahertz receiver. Now this is like as you can see, this is a multi-frequency probe design. This is multi-frequency probe. As I said you before, also there is they had used one in 1.4 gigahertz system. They had used a technology for calibration. HFSS is a commercial infinite element method solver for electromagnetic structure, and it's developed from NES, and and this HFSS stand for high frequency structure simulator, is one of the several commercial tools used for antenna. It is used for antenna the design of complex radio frequency electronic circuit element, including filter, transmission line, and packaging. And this as you can see in this figure, uh, there is a three graph mention there is three graph mention, and This is a comparison measured between two HFS simulation uh, for figure 1.4 gigahertz, and second figure is 2.7 gigahertz, and the third one is 4.9 gigahertz when probe is used. And while using this, the scope for this thesis was to estimate, while be done with a water phantom, it is necessary to demonstrate that hardware can be designed for the actual application for non-invasive medical radiometer, and the example was shown in section that was I mentioned in previous slide. And it is quite for a single frequency to multi-frequency must be used to differentiate temperature received from the various depth in the tissues, and the additional challenge is that the probe must be receiving power from the same part of tissue, or at least in the manner that ensure the model is still valid. This model assumption is that the tissue are stack of homogeneous tissues layer that infinite in extent and in transitive direction with the uniform temperature in the transfer direction. This is the three layered which was used to in that all the probe design to measure the temperature. Normalized weighting function was three frequency probe on three layers, and medium of the skin was 1 millimeter, fat was 2 millimeter, and the muscles skin, fat, muscle, feed, radiator, as all the digits are mentioned in this figure. You can just see this figure. It's clearly mentioned whatever is used in different uh, system to measure the radiometric frequency temperature. And this was the and this is and in this figure, SAR at a various depth in the tissue of each of three probe, like what was used in system 1.4 gigahertz to and in 2.7 gigahertz and 4.9 gigahertz each individual SR slot. This is SR slot is used to normalize to a peak value as demonstrated by a scale. It is it can be seen from the SAR slot close to the being to occur in the center of the entire probe footprint. Skin, fat interface, fat muscle interface, 32 into muscles. Now I'm going to just conclude this thesis chapter. Uh, in this, I have mentioned all the necessary receiver architecture. I have mentioned in my previous slide, and relevant design equations of and there was a equation in this thesis also for designing a radiometer for non-invasive microwave thermometry to address the problem of operation in the conjugate RF environment. Narrow frequency band allocated for remote sensing and radio astronomy were utilized. Two radiometers were presented and the performance characterized. In addition, probe for use with water phantom were shown. Additional multi-frequency probe for medical application were categorized, and then it is measured and simulated. As I said, they had used HFSS software for designing antenna and other micro radio frequency and everything to simulate performance, and simulate performance and compared with all the three system 1.4, 2.7 and 4.9. Now I am going to explain the another thesis which I had uh, gone through. Now this is the another thesis, and in this thesis previously I have completed two chapters. This is the third chapter I'm going to explain in this presentation. I have previously studied both the chapter, and now I am studied this third chapter, which is near field antenna probe, how the probe is designed and whatever the things are mentioned in this chapter. This In this there is a microwave radiometer thermometer. The probe received thermal power radiated by the tissue. However, standard antenna design and analysis is not directly applicable since the probe is in the near field of tissue. As you can see in this figure, there is a skin, fat, muscles, and the probe is at the top of the tissues, and a near field probe positioned on the stack of a skin, fat, muscles, and there is a high you can see in this figure there is a high dielectric constant between a tissue and the high conductivity of skin and the muscle layer result in the attenuation in tissue layer. And you can see in this second figure, that is B, there is a probe need to be engineered to receive a large proportion of power from the muscles layer while minimizing the reception from the skin and the fat layer electromagnetic properties of the tissue. As I have mentioned that given at 1.4 gigahertz. And next is this is a table uh, which all the probe of microthermometer which from literature, and the frequency is defined in this. You can see in this table there is a different architecture was used, and dimension, the specific dimension for every architecture, and they had near field loading for the in which tissues they have applied, and in which environment they had uh, uh, tested this, and it is all mentioned in this table. uh, Now there was a subtopic in this probe design also, that they had a uh, now and one more thing I have forgotten, that they had used HFSS technology, electromagnetic simulation tool, or a SIM full life used to determine a probe sensing pattern. And during this designing process, the volume loss density was simulated at all point in tissue stack to maximize the absorbed power density in a buried muscles layer. As you can see in this uh, 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 I'm just previous going to just explain. I have forgotten some points in this. There is a considering a probe was on a stack of skin, fat, muscle layer, considering the boundary condition of electric field vector and high dielectric constraint between skin, fat, and muscle layer. And then after that, there was a circular in this thesis there are subsection in designing in near field probe, in near field antenna probe. There was a circular patch. In this circular patch, as you can see, there is one figure. This figure is about simulating a circular patch probe reflection coefficient when placed on the stack of skin fat muscles and and uh, and simulate low power loss density for circular patch probe placed on the body model, and then the probe is fed with 1 volt match power. According to this, the patch is placed on the tissue stack and fed 1 volt match source a full wave simulation using HFS is the resulting the result 1 second for yes no as I was saying that in this figure they were using HFS technology for full wave simulation, and that results in volume power loss density cross section at the center under a probe shows that 33% of total probe is absorbed in the muscle layer while the skin layer absorbs 50% of the power. It can be seen that larger fraction of power is absorbed in the fat layer, although it has the lowest loss. This is due to large mismatch in the real part of primitive between fat and neighboring skin and muscles. Now in this there was another design that they had used that was a circular patch with super strict. In this the volume loss density of circular patch with and without super straight are compared. You can see in this both there is a figure A and B. They had used volume with and without patch also, and the patch is designed first I'm going to explain this first figure. The patch is designed to maximize power desorption into a buried muscle layer, and in B section this figure adding appropriate substrate match the probe to deeper tissue layer and double the power transfer to the muscles layer. In simulation 2 and 5 centimeter is used to skin as a skin and muscle phantom, and 5 FR4 is used as a fat phantom. And the another patch was circular patch with they are using with another uh, different circular patch with super straight and short pin loading also. They had used a circular patch with super straight and short pinning, um, that measure impedance matching when the probe is placed on the body, and two layer phantom also were used in this of 2 of smoked salmon. And now I'm going to explain this figure. As you can see in this first figure, there is a circular patch probe in with the super straight and shorting pin, and in figure you can see a photograph of fabricated probe layer, a short pin circular patch covered, and there is a major impedance matching when the probe is placed on a human body to a two-layer phantom consisting of 2 of smoked salmon, representing skin saline, as well as 3-layer phantom consisting of 2 skin, 1.7 meter Roger to 6.10 fast and saline. And there is a array patch probe also considered in this array patch. There was a circular probe with superstate and used the same as before, supersting pin, and then fabricate, and then you can see in figure next to that figure B, fabricated array of rogers was used 6010 to 1.7 mm measured of array is compared to a single element when both the probes are located on the stack of 2 mm agar to the 3.81 mm fat and selling muscles. And now next was slot probe with super string. In this you can see that small table architects ring slot and in flower stalk, uh, various skin fat muscles is used and what the exact amount was used measured accordingly. And you can see in this figure this 3.13 slot architects by nature provide a strong tangential uh, E field at the interface of skin probe with which does not attenuate at interface of tissue layer. Different slot of probe are used to simulating the same HFSS technology and compared in the term of matching the power and power disposition in the different tissues. Ring slot probe can provide strong power deposition in muscles to reduce the size. A Mender shape ring slot, flower slot is designed to reduce this slot, reducing the power reception from muscles layer. Now, molding and modeling analysis and validation is done. Uh, when uh, when stimulated normalize volume power low density volume v vpld of probe placed on the stack of skin fat muscles in hfss and sim for life. vpld is shown at two coordinate under the center and under the edge of probe also. I have also attended this HFSS class to design an antenna on previous week, and I have also learned this thing how to simulate and basic thing how to use this software HFSS. And now again the class will be held on Wednesday, and I have also attended Monday meeting also. Next was the influence of layer thickness variation on temperature estimation. This is like this is the probe placed on the stack of skin fat muscle thickness of skin and muscles are 1.2 mm and 5 centimeter, and the fat thickness is varied from 2 to 8 mm. Weighting functions are obtained from same uh, sorry same software HFSS, a simulation electromagnetic properties of tissue presented in chapter 1. And as you can see this graph is a uh, estimate muscles temperature compared with real muscles when it varies to 35 to 39 degrees Celsius. Estimate muscles measure does not deviate from real muscles temperature more than 0.6 degrees Celsius. For fat variation of 2 mm to 8 mm. And you can see in this above table they had defined all the frequency, fatness, thickness, how much fatness, thickness, and what frequency, and a particular specific fat, skin, and fat weight, muscles, everything is specified in this table. And when the probe is uh, probe placement, when probe is placed on a centrum, how the temperature is differed and how we can measure, uh, and there was average thickness, electromagnetic properties, and weighting function of tissue layer when probe is placed on centrum. When a probe is placed on the centrum, the tissues is skin, fat, cortical bone, cancellous bone, and cortical cortical bone, and heart. Then comes to heart, and in this the average thickness was mentioned is this, and dielectric constant, and conductivity, and then a wave frequency. This they had when probe is placed on centrum, there was a six layered and simulation for this simulation of volume loss density weigh upon meters on the stack of skin, fat, and rib, uh, composed of cortical, cancellous, and cortical bones, and then heart, and then comes the heart. And same when probe is placed on the forehead, different tissue layer are there, and there is a average thickness, and for every tissue there is average thickness is defined, electromagnetic properties, and weighting functions, and then everything is defined. In this simulation, volume of loss density on the stack of scalp, skull, cancellous, and cortical bones, and then comes the brain. There are also for measuring forehead temperature when probe is placed. There is a layered called scalp, skull. Skull is also divided in three sections like cortical, cancellous, and uh, cortical, and then comes the brain, like this. Uh, now I'm just going to summarize everything which I have gone through in this thesis and this chapter. It's quite amazing to summarize, and it was quite interesting topic in this thesis, and it was important for the studies also. Now I'm going to quickly summarize all the things which I have discussed previously. In this chapter, the probe design for basically for human body microwave thermometer that results into towards designing a near probe capable of detecting small temperature variation of deep tissue layer, and then there was several near field probe matched of a stack of skin, agar, phantom fat, fr4 subtracted, and muscles, agar, phantom are designed, and then there was a circular patch as a RFI shield planner design, and substrated is then added to improve the performance. And finally, shorting pin inductive loading is added to reduce the size of the patch. And then the patch was 2 into 2 array. Minimized probe is then designed as a 1.4 gigahertz to 1 power cabin was designed to combine the thermal noise received from all the probes. Several slot architecture was also examined at the same tissue stack, and substrated slot architecture have higher bandwidth and receive high amount of thermal noise from the muscle layer, making them more susceptible to RFI, while patch structured, have the advantage that the ground plan allow for a easy integration with the radiometer circuitry, also minimize that amount of RFI. And this probe was designed through simulation with commercial full wave FEM simulator used HFSS and volume power loss density in the tissue layer from the different probe are compared, and the design are validated with the FDTD commercial code and measurement and near field pattern of circular patch with the superstrate and short spinning and measured a reciprocal. And you can see in this figure also there is a comparison, and almost there are 8 architectured in this mention in this thesis. And the effect of the tissue thickness variation in temperature retrieval is analyzed, and finally the probe placed on the centrum and the forehead as discussed. I discussed this in previous slides, increasing the fat thickness shown to the reduce the overall received power by the probe. This issue which can be solved by using an array. And next, thank you for the day. And one more thing, I have also attended Monday. I am always attending Monday meeting, and that HFSS course class, that is software to design an antenna. And thank you for the day.